So we'll now talk about computing this complexity, in particular in the case of worst case asymptotic time complexity. So for this, we'll need to introduce new notation called the big O notation. So what is it useful for? Well, it's useful to quantify the complexity, the use of resources. So we'll count the number of steps or the amount of memory or time that is needed to execute the algorithm for an input of given size n. And it will express, so we'll first express this number of steps or memory or time. We'll express this as a function f of n, where n is the input size. Now, what do we care about in this f of n? Well, if I tell you that computing power evolves very fast, it actually doubles every 18 months according to Moore's law. So this is an informal law that says that the computing power doubles every 18 months. So this is informal, but it was observed a long time ago, I think in the 60s maybe, and it has held true since then. So every 18 months, pretty regularly, you've seen that computers have doubled in computing power. Now, it's a self-fulfilling prophecy in some ways because processor companies, so companies making processors, sort of expect this prophecy to remain true, so they plan their business according to that as well. So it's a self-fulfilling prophecy in that sense. But anyway, computers are evolving in power every year, every 18 months, they're doubling. So this means that as soon as you have f of n that has, as soon as you determine the rate of growth of f of n, the general rate of growth, that's what matters basically. Because if you're looking at little constants or little little factors below the main one, this is likely to be very unimportant very soon. So what I mean is that here, I repeat this, the scalar constants don't matter too much. What matters is the exponents that are present in f of n, for instance. So if you have f of n equals 3n plus 1, well, this 1 is not important, and this 3 is not important. But if you have f of n equals 3n squared plus 1, then this 2 is important, and so is the one that is that I didn't write here. Or if you have f of n equals e to the 3n, then this 3 is important as well. Okay, so what is actually, how do you extract what is important? Well, for this you invent the big O notation. So you say that fn is in big O of g of n, if and only if the lim sup for n going to infinity of f of n over g of n is less than infinity. So it's bounded by a constant. There exists a constant c between 0 and infinity such that f of n is less or equal to c times g of n for large n, for large enough n. So you could say that 3n plus 1 is in big O of 3n plus 1, but you haven't won anything by saying this. So let me write this down. So if f of n is 3n plus 1, then yes, f of n is big O of 3n plus 1. But you can also say that it's big O of 3n because you quickly see that this 1 here does not matter when you compute the lim sup. But it's also big O of n because the constant here that the lim sup equals to is not important either. So in summary, f of n is big O of n. Well, if f of n was 3n squared plus 1, well, you could do the exact same reasoning and say that this is, oops, I miswrote. This is inside, so in big O of n squared. And if you say f of n is e3n plus e2n plus n squared, then looking at the lim sup definition, you know that this is in big O e3n. So it helps you select the leading order term, and that's what's important in the big O notation. Okay, so let's see an example of this. Let's say I'm trying to find someone in the phone book, and I'll give you two different algorithms and try to give you a flavor of why one is better than the other. So here's the first algorithm. I want to find a name in the phone book, so what I'll do is I'll look at the first name, look if that's the one I'm looking for, and if not, go to the next one, and so on, all the way to the end. Okay, so if I was to look for my name, for instance, Dehaye, I would start at quadruple A or something, and look at it, and that's not right. Then go to the next, go to the next, go to the next, go to the next, etc. up until hitting here the jackpot, and I just found my name. So you can see that this already feels pretty slow. But what's the worst thing that can happen? Well, the worst thing that can happen is that you're named ZZZZZ, or your name starts with Z, and in that case, you have to go through the whole phone book to find the name. So if the phone book is of size n, what you need to do is go through n steps. So in that sense, it completes in O of n in the worst case. So that wasn't very effective. So let's see if we can improve on this. So here is a second algorithm to find a target name in the phone book. The algorithm goes like this. You look halfway in the phone book. You just split it in two, and you compare the entry on that page with your target phone number or your target name. And you just decide, is the name that I actually want on the left before or on the right after? And once you have made your decision, you discard the wrong part of the phone book, the one that's useless to you. Now you have half a phone book and you iterate, you do it again. So you split that half of the phone book into quarters and you decide in which quarter to look. So this will complete much faster. Let's see again an example where you're looking for my name. So I'll look halfway in the phone book, and let's say I decide on this being halfway. So is the name Dehaye before or after? Well, it will be D before H. So I can just ignore that whole part of the phone book, and I have to look into this part. Now that I'm looking into this part, I split it in two, and I have to compare Dehaye with DA. Now, I know that Dehaye will come afterwards, so I can just ignore this. And I'll look halfway, and here I'm lucky, I actually fall on my name. So in 3 searches, I have immediately hit upon my name. What could happen in the worst case? That you should immediately ask yourself. Well, each time I'm discarding essentially half of the phone book, okay? And I'm performing one operation, the comparison here, and then I'm looking for the name. I'm doing the same thing, but on an input that's half the size. So in other words, the time it takes to complete the task for an input of n will be 1, because I do one comparison, plus the time it takes for an input of size n over 2. Okay? So let's say for a minute that n is equal to 2 to the a. So then what this is saying is that f of 2 to the a equals 1 plus f of 2 to the a minus 1. Okay? And then f of 2 to the a minus 1, well, that would be 1 plus f 2 to the a minus 2. So this is 2 plus f 2 to the a minus 2, and so on, and so on. Right, because those are powers of 2, so you can iterate again and again and again, all the way to a phone book of size just 1, where you have just one name isolated. And how many times can you do this? Well, it will be the log in base 2 of n. In other words, here, a. So what this is saying is that when n is equal to 2a, then f of n is equal to a, which is the log in base 2 of n. And in general, that's the case. If n is between 2 powers of 2, well, that's the other option. Either it's a power of 2 or it's between two powers of 2. Then you just approximate by the highest one of the two, and you realize that it will be essentially like the logarithm. The logarithm does not change very much between 2 powers of 2. It changes by at most 1. So in other words, f of n is in big O of log in base 2 of n. And actually, you realize quickly that this 2 here is not important because it's just a constant. And remember, the limb sup was computed regardless of the constant. So I can just say that f of n is big O of log n, or is in big O of log n. So this was not very visible for the size of the phone book that I had. Okay, I couldn't have a much bigger phone book on my slide. But if you had an actual phone book of the size of the city of Zurich, you can immediately see the advantage, right? You're naturally already performing this algorithm, but in practice, if you were to do in practice with a real phone book, the previous one, you would never find the name. You would never find me, right? Because at D, you would have to go through already a substantial part of the phone book. So that was the second algorithm. And you can see, thanks to this evaluation of the complexity, that we've formalized the fact that this algorithm was much better than the previous one.